Hi, in this lesson we are going to look at hidden Markov models or HMMs. First, let's look at some speech recognition basics. Speech recognition can be accomplished using the popular template-based pattern recognition approach. One key idea here is to derive typical speech sequences as patterns, example word patterns, and calculate local spectral distances to compare the patterns. Even though statistical techniques are widely used in clustering to create reference patterns in image-based techniques, it is often inadequate for speech classification and recognition. Consider, for example, the use of LPC, linear predictive coding of speech segments, as a distortion measure for the local distance of the template matching. The Euclidean distance form of the LPC coefficients suggests that the reference vector can be viewed as the mean of some assumed distribution. This simple form of sufficient statistics neglects the time dependency of speech signals, which is often very useful in recognition speech utterances. So, we need to study a more elaborate and analytical statistical method for speech recognition, which will take care of the time dependency of speech signals. Later we are going to look at a more widely used statistical method of characterizing spectral properties known as hidden Markov model or HMM. Let's here look at the functioning of a discrete time Markov process. Consider a system that may be described at any time as being in one of a set of capital N distinct states. At regular spaced discrete times, the system undergoes a change of state according to a set of probabilities associated with the state. Here we denote the time instance associated with that which states changes as t equal to 1, 2, so on and so forth, and actual state at time t at qt. Qt's are the states. There can be state q1, q2, q3 like that. A first order discrete time Markov chain depends on the previous state only, just only the previous state. If you take a probability qt of a state given qt minus 1, the previous state, comma qt minus 2, two state before the current state, like that you can have qt minus 3, so on and so forth. So qt is j state, qt minus 1 is I state, qt minus 2 is kth state, like that you can define it. That is qt given qt minus 1 comma qt minus 2. But if it is a first order discrete time Markov chain, then it will depend only on the previous state, that is qt minus 1. That means qt minus 2 can be dropped here. That means this statement can be reduced to probability of qt given qt minus 1. So we can also write p equal p probability j given I. J is the current state, I is the previous state. The state transition probabilities aij is given by aij probability of qt given qt minus 1. Qt is equal to j, qt minus 1 equal to I for all I and j between 1 and n, with the following properties, where for all actually I and j should be greater than 0, and for all, that is for all I and j, aij, the transition probability is always positive, it's a probability, and also if you sum up all the transition probabilities from 1 to n, it should be equal to 1 for all the nodes in the Markov chain. Let's take an example here, which is a weather model. We have three states here: rain, cloudy, sunny. Rain is state 1, cloudy is state 2, sunny is state 3. So let's assume that once a day, example at noon, the weather is observed as being one of rain, cloudy or sunny. The state diagram is shown, and then these are the state transition probability, that is, if it is a rainy day today, what is the probability of next day is also rainy, so it's 0.4. Rainy day next day is cloudy is 0.3. Cloudy day next day is rainy is 0.2. So this is a model that you can create by observation of several days, and then come up with a statistical table, and then put this in a diagram form. And then we can also characterize actually the weather on day t is characterized by a single one of the three states given by this matrix. So same thing given here. So we have this figure here, or we can have it in a matrix form. I current state, j is the next day. If it was a rainy day, next day is a rainy day is 0.4, rainy to cloudy 0.3, rainy to sunny 0.3, so on and so forth. Also we can write it in matrix form. Aij is equal to the matrix equal to Aij transient probabilities. Now the question here is, what is the probability that the weather for 8 consecutive days, sun, 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 rain, rain, sun, cloudy, sun. So if the state sequence is given, we need to find out what is the probability of having such a state sequence. Let's see how are we going to attack this problem. So what is given here is the observation sequence, which is the sunny, 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 rain, rain, sunny, cloudy, and sunny. So sunny state is state number 3, rainy state is state number 1, cloudy state is state number 2. So basically we have this observation sequence of the states. And now we are going to write an equation for probability of the observation sequence given this kind of a model is given by this equation. That means the state transition qt given qt minus 1, if you are going to have n states, in this case there are 8 states, 8 days, so go from the first state to number 8, day number 8. So you have to this pi means you have to multiply the probabilities, not addition. If you had a sigma, you add. Here this is pi, means multiply. Okay, this is the answer to this question, where the probability of the observation sequence given the model, we have state 3 3 3 1 1 2 3 2 3 given the model, and the first probability is the initial probability p3. Actually p3 is we use the notation pi I, which is the initial denote the initial state probability. That is, we have 3 states, and out of those 3 states we are going to select one state to start with. So this is we have to start with the sunny state, so p3, and then after sunny state is given, what is the next state? 3 given 3, 3 given 3, and then next day 3 given 3 again, probability of 3 given 3, and the next day 1 given 3, that is we know a sunny day here, and then it's going to jump into a rainy day. So this is 3 is given 1 given 3. So sunny day is given, what is the probability of getting a rainy day? And then 1 given 1, 3 given 1, 2 given 3, 3 given 2. So these are the few probabilities that you need to multiply together to get the total probability for this kind of state sequence. So when you substitute, and please note that here we take the initial probability equal to pi 3 equal to 1. In some cases we assume 1/3. If you have 3 states, there is equal chance of selecting the first state, but here we take pi 3 is to be equal to 1, and then the other state transition probabilities are given from the matrix. Then they substitute that and we get this probability. So this is how we calculate the probability for a given sequence. But in this case these sequences are observable, basically the states are observable. So the Markov model is a process in which each state corresponds to a deterministically observable event, and hence the output of any given state is not random. So sometimes we cannot use Markov models are too restrictive, therefore we cannot use to for speech recognition applications. Then we are going to look at something much more elaborate called hidden Markov models. Here we extend the concept of Markov models to include the case in which the observation is a probabilistic function of the state. That is, the resulting model is a doubly embedded stochastic process with an underlying stochastic process that is not directly observable, hidden, but can be observed only through another set of stochastic processes that produce the sequence of the observations. Basically, it's the speech processing in which what we normally see is the speech, the sounds, but we can't see the state or the word the, at uh, uh, which state the words are. There are several models that we define. So what we see is only the what we observe is only the speech signals. Let's see how we are going to apply that hidden Markov model for speech. Let's see what the theory of hidden Markov models, and then we redefine the coin toss model in a little bit of different way. In this case, we have assume that you are in a room with a barrier, example a curtain through which you cannot see what is happening. That is, we are in a room where there's a person behind the barrier and then who is tossing a coin. On the other side of the barrier is another person who is performing a coin tossing experiment using one or more coins. The person will tell you which coin he selects at any time. He will tell you only the result of each coin flip. Thus, a sequence of hidden coin tossing experiments is performed with the observation sequence consisting of a series of heads and tails. Hence, the following sequence can be observed. That is, the observation is something like that, but we don't know whether he tossed one coin, two coins, three coins, but he only tells that he got a head or a tail. So, in this particular case, we can think of three models or more. In this case, it can be a one coin model or two coin model or three coin model or more of them. So since the number of coins tossed is unknown, so just what we know is that after tossing a coin he will tell whether it's a head or tail. So let's look at it as a one coin model. So that means we can predict there is a head or a tail as two states. So whenever he get a head, that means state 1. Whenever he get a tail, it states 2. So basically what you see here is a one coin model, which is an observable Markov model, because whenever the person tells that he got a head, we can obviously tell which state he is in, because head is the state 1, tail is state 2. So therefore it's called observable Markov model. It's not hidden. The states are observable. So whenever you look at the observation, we can tell what state the coin is, whether it's in the state 1 or state 2. So here is only one unknown, that is the probability of coin toss. It can be it is a bias coin, therefore ph is not equal to p tail, so 1 minus ph is not half. Okay, let's proceed further and look at a two coin model. That means behind the curtain there is a person who is tossing two coins. So in this particular case, we can assume that the state 1 is the coin 1, state 2 is the coin 2, and therefore there are four unknowns here. That is a11, a22, 1 minus a11, 1 minus a22. So there are four probabilities that is unknown. That is the probability of tossing coin 1 and getting head, probability of tossing coin 1 getting tail, similarly for coin 2. So what we get now from this particular model is that these are the outputs. So what happens is that the person tells you that he got a head, tail, head, tail, whatever sequence, but you cannot predict the state, because what he tells is he got a head. It can be coin 1, it can be coin 2. So therefore once you get heads, you can assume that okay, it may be state 2, it may be coin 2. Whenever he tells that he got 1 because he has the choice to select either coin 1 or coin 2. Basically here the physical mechanism which accounts for how state transitions are selected could itself be a set of independent coin tosses or some other probabilistic event. That means the person can select coin 1 or coin 2. Before he select coin 1 or coin 2, he can toss another coin to find out which coin he wants to select. So it's another probabilistic event. That means he toss another coin. So if he get tail, okay, I will toss coin 2, and then he will tell the output of tossing coin 2. So next time he want to toss another coin, he toss a third coin and then see which one he wants to select. So like that, there is another probability, the second probabilistic behavior to select the states. So whatever you got here is a hidden Markov model. That means by looking at the observation, you can't tell the state. It can be either coin 1, can be coin 2. So that's why we have here, it's not the same number here. Head can be 2, head can be in state 1, tail same thing for tail. Okay, the things will be more complicated when you come for a three coin scenario. Again, we have lots of probabilities, about 6 probabilities that are unknown, actually 9 probabilities that are unknown. So these 9 probabilities can be calculated by observation, and also here we get a few observations here, and again what you can see, it is a hidden Markov model. That means by observing, that means he has 3 coins behind the curtain and toss the coin and tell the output. So he get head, tail, whatever. So this is coin 1, coin 2, coin 3, but we don't know which coin he was tossing. So therefore head can be from coin 3, this head can be from coin 1. So the selection of the coin 3 or coin 1 depends on his arbitrary probabilities given by another stochastic process. Okay, let's now revisit the weather problem. Now suppose that you were locked in a room for several days and you were asked about the weather outside, which is similar to the coin tossing problem. That means in the coin tossing problem, we didn't know what is behind the curtain. So what we know, only the observation. Here similar thing happens, that is you are in a locked room, you don't know what is the weather outside. So you need to have some observation. The observation in this particular case is the only piece of evidence you have is whether the person who comes into the room carrying your daily meal is carrying an umbrella or not. So a person comes to give you a food, maybe you're locked in the room, so he brings an umbrella depending on the weather outside. That's the observation. So using that observation, there can be a possible probabilities. That is, if it is sunny day, is highly unlikely he bring an umbrella, so less probable. But if it's a rainy day, he brings an umbrella. If it's a cloudy day, he might bring an umbrella. So depending on the day's weather outside, he brings an umbrella. So the probability of bringing an umbrella depends on the weather. So now our question here is that we are going to model it in a Markov process, and it's actually a hidden Markov model. So here we'll assume the assumption here, that means the probability of observation given the model, again same thing that we saw earlier, qt given qt minus 1, and now we have to factor in the fact that the actual weather is hidden from you. Here we do not do that by using the base rule. In this case we modify the base rule to accommodate for observations. That is, this is the observation. That is basically, normally we write base rule, a probability of a given b equal to probability of b given a times probability of a divided by probability of b. So in this case, probability of a given b are the observations. So that means if I see an observation, what is the probability of getting any of these states, and then it can be modified by this same thing can be calculated by using other values of the probability. This is probability of b given a times probability of a divided by probability of b. Okay, Let's continue further. Here ui is the observation is true if your caretaker brought an umbrella on day I and false if the caretaker didn't. So there is an event ui depending on the observation umbrella. If there's umbrella, that means it's true. If there is no umbrella, it is false. There's a half probability of 0.5. The probability p, the observation given the model, again we saw this one probability which is given by this equation here is the same as the Markov model. So the probability pu1 un is the prior probability of seeing a particular sequence of umbrella events, true, false, true. The probability u given q is actually observation given the model can be estimated as pi t equal to 1 to n put given qt. If you assume that for all I given qi, ui is independent of all uj and qj for all j is not equal to I. These are two independent events, that is given qi and ui is independent. That means the observation sequence is independent of the previous day's weather. Only it depends on the current today's weather. Here's the problem. Suppose the day you were locked in it was sunny. The next day the caretaker carried an umbrella into the room. Assuming that the prior probability of the caretaker carrying an umbrella on any day is 0.5, what's the probability that the second day was rainy? Again we have this table, the probability, the distribution, the state transition probabilities for the rain, cloud and sunny days. Apart from that we have the extra probability table which is the umbrella observation, and now we need to solve this problem, what we have to find out is the assuming that the prior probability of the caretaker carrying an umbrella on any day is 0.5, what is the probability that the second day was rainy? So the first day we know it was sunny, but we need to know in the second day we are not able to see outside, but only we can see the probability of bringing the umbrella. So caretaker brings an umbrella, so we need to find out the probability of the second day is a rainy day. So if it is, what is the probability of the second day is a rainy day if there was an umbrella event observed? So okay, so that means the q1 is the state 1 is sunny, q2 is state 2 rainy, that is the second day. u2 is the observation sequence, that is the second day we observe there's a true umbrella event, and if it is true we normally take it as 0.5. And we can write an expression here, probability of q2, that is the second day, given first day sunny and observation event u2, second day you see an umbrella. So these are the two things that we know. We know that q1 was sunny, u2 is the observation sequence of the umbrella. So we need to calculate this probability. What is the probability of q2 given q1 comma u2? And we can use simple probability techniques here. Please note that this is like a given b, this is a comma b, divide by probability b. So u2 is common here. Basically this is the observation sequence. Please note that this is coming from the rule probability of a given b is equal to probability of a comma b divided by probability of b. So please disregard u2 in this particular case because u2 is common to all these expressions. So basically we are considering only q2 and q1. So q2 is a, q1 is b. So a given b equal to p a comma b divided by pb. So what we are going to do is we are going to simplify this expression to find out whether we can substitute the known probabilities and calculate this value. So here we we separated this one into two parts like this, and now we have another statement here. Since u2 and q1 are independent, we can write that is u2 is the the umbrella event in the second day, which is totally independent of the weather in the first day. Q1 is the weather of the day 1, which is sunny. So it is there are two independent events. Therefore, this expression we can remove this condition. Basically, probability of Q1 given U2 is equal to probability Q1, because Q1 does not depend on U2, which is an independent event. Therefore, the denominator will simplify to PQ1, probability of Q1. The denominator is same. Okay, so let's take it back to the next page. This is what we got here. We are up to here now. So we want to simplify this further because we still can't substitute values. What we want to find out is this one, but we got up to here, but still we don't know this expression, how to simplify this one. We know this expression. Okay, let's take this one out, PQ1 out, but we need to simplify this part, P probability of Q2 comma Q1 given U2. So this one again we can write an expression for this one. Again, if you look at this one carefully, what we have here is A given B, A given B, A times probability of A times probability of B given A divided by B. So basically this is base rule. That means we now take the probability A to be Q2 comma Q1. Please note that this is, just assume this as one variable given U2B, and probability of A times probability of B given A divided by probability of B. So basically Q2 comma Q1 is A, U2 is B. So using the Bayes theorem we can simplify this expression, which was difficult to calculate. So we calculate, and this part is still same, 1 over Q1, 1 is probability of Q1 is still remains outside, and then we get this one, and then we have this formula. Okay, now we again have a condition of first order Markov assumption. That means we have this expression, we write it down here as it is. This is the same thing that you've got from here to here, and from here we write the same thing. And now we have the first order Markov assumption, means that we don't have to worry about this. When you look at here, this expression here, the probability of the umbrella event, today's umbrella event, only depends on the day's weather here, not the weather the previous day. That means U2 is given Q2 comma Q1. So Q1 is independent. So you don't have to consider, because it's a first order Markov chain. If it is second order, need to consider the previous day, but therefore Q1 can be removed. So this is because of the first order Markov assumption. Okay, now we have this little expression here. So we still have some doubts to replace. So we'll go further to get rid of this PQ2 comma Q1, because we have this PQ2 comma Q1, which is we still cannot find out. So what we do is we separate it out and we put the other things together. This one of course we should be able to calculate, but PQ2 comma Q1, again we can use the rule P probability of A comma B is equal to probability of A given B times probability of B. These are some variations of the Bayes rule. You can easily find out this one. Basically probability of A comma B, that means if you have two dependent events, if you select the first event A given B, if you select the first probability of B and then multiply by the second event, that means if B given, that means what is the probability of A. So this is you can calculate this one. That means if you choose a object from a random collection, then after taking one of the items from a collection of balls, so if you don't replace that ball, that means we take that B is taken. So that means after B is taken, what is the probability of A? So basically it depends dependent events. So you have to multiply. This is a rule that you can easily show from the Bayes rule. And then so basically we have this expression Q2, that is A comma B, probability of A comma B can be replaced with probability of A given B times probability of B. Okay, so now we have a cute little expression now. That means once you substitute these values, we can get rid of PQ1. PQ1 will go off, and we have this simple expression now. That means once you substitute PQ2 comma Q1 with this expression, we have PQ2 given Q1 and PQ1 cancels off, and times PU2 given Q2 divided by PU2. Okay, so this is our simplification. Now we put the variables here. What is Q2 is the rainy day, Q1 is a sunny day, probability U2 is true event, Q2 is a rainy day, and U2 is a true event. So that means we have this probability of Q2 given Q1. That means the probability of a rainy day given the previous day of a sunny day, 0.1. This is coming from the previous table, so that we know from the diagram. Probability of rain given sunny, and then this one is given again. That means if you observe an umbrella event given a rainy day, in a rainy day there's 0.8% chance of bringing an umbrella. I think I go back again to show those things to clear up the mind. So it's given here, this is the umbrella event. That means if it is a rainy day, the probability of bringing an umbrella is 0.8, and the previous day was a sunny day, and bringing and coming to a rainy day, second day, is only probability 0.1. Sunny to rainy is 0.1. So these are the values that is substituted in this expression here to finally find out the probability. So yeah, so this is what we stopped at. So this is 0.1 times 0.8 divided by 0.5. This is actually given. That means if you observe a true event, we have a 0.5 probability, either can be true or false. Okay, so finally we get the answer. Therefore, assuming that the prior probability of the caretaker carrying an umbrella on any day is 0.5, the probability that the second day was rainy, 0.16. That means Sunday is the day that you locked up, and the second day you saw an umbrella event, and then the probability of that day to be a rainy day is 0.16. It's again a very simple example to show by using the observation how are you going to predict the state of that particular thing. Okay, now let's get away with this umbrella events and hidden coin tossing experiments and such for a moment, and talk about real things like speech recognition. So what we saw for the umbrella event, actually the weather problem, that is, there were 3 states and there were some probabilities depending on the states. So what is the relationship of that to speech? What is the observation actually? Basically we had an umbrella observation depending on the state, and it is very simple. Like if you relate this to this, basically in the speech you speak a certain utterance or a certain word or certain sentence. So it creates a waveform which is the state actually. These are the states, and what you observe is the speech waveform. Basically these states will give us a speech vector, so that vector is the one that you observe. These are the observations. So once you have the observation, basically these vectors will tell us a certain amount of information about the state at which that particular speech model, basically when you write a expression for this transition, that means if it is a word, there are some phonemes. There can be several ways of pronunciation, like one way like that, another way like that. So these are some states. So the states are the phonemes, which are actually how the words are made out of. But we can't see that actually. These are the states. We only see the speech that you listen, the vector. So these are the speech vectors that is coming out. So use these speech vectors to predict the states and tell this is what that person is pronouncing. So there is a prediction which gives us the phoneme, and then gives the word, and then gives the sentence. Okay, so basically what we do here is that in speech recognition the basic idea is to find the most likely string of words given some acoustic input. That means what we see is this acoustic input vector. So using those acoustic input vector we predict the words. So that means we need to maximize the probability, this condition, argument maximization of a certain word, string of words, a certain language. W is the string of words. So we have the string of words. If you, that means given the acoustic, that is this is what you hear, and use that to predict W. So W given Y. So we listen to Y, use the vectors to predict W. So where the W is the string of words, L is the language you are interested in, and Y is the set of acoustic vectors that you have gotten from your front-end processor. The front-end processor is typically an n-dimensional vector. These are the vectors of the speech vectors. It can be LPC or maybe some other technique that you extract the feature vectors, and which represent 10 to 20 milliseconds of speech. A typical value for n is about 8 to 40, depends on the system. So you take a feature vector and then use that feature vector to predict W. So this is good. Feature vectors are the observations. So basically that's what we saw. The observations are the, in the previous case it's an umbrella. So use the umbrella. If you see the umbrella, then you should be able to predict the weather. Similar to that, you can predict the, in the case of speech systems, acoustics are our observations similar to the umbrella, and the words are similar to the weather state on successive days. So the basic equation of speech recognition is Bayes rule. Again, Bayes rule. So we want to maximize this one, but instead of using this equation we can use the equivalent equation P y given W times PW divided by Py. This is basic equation. Bayes rule for a single speech input, example one sentence, the acoustic Y will be constant, and therefore Y so will Py. So acoustics are constant, therefore Py will be constant, and therefore we need to maximize the argument of this one, Py given W times Pw. Okay, let's see a simple model, simple word model here. So this is a diagram of a word model, which is what we were just going around, and these are the states here. Basically it is a simple word of how to pronounce the word. Can be several ways, in this case 2 ways of pronunciation, and then we end up with a model here. So the Py given W is called the model likelihood. That means if you y is the observation, what is the given the word. So if the word is known, what is the observation pattern Y, and Pw is called the prior probability of the word string. In the case of the word pronunciation, Py given W is the probability of the acoustic given the word. So if you know the word, what is the probability of that particular acoustic. Note that many acoustic vectors can make up a word, so we choose an intermediate representation, the phone or phoneme. So basically a phone can so many acoustic vectors can make up words. So that means you can pronounce the word off in several different ways, so still it will make the word off. So what we did in our experiment is that we did like we can do record that observation of, say we pronounced the word off 100 times, and out of 100 times 71 times we can think that it will follow this part of the model, and 29 times it follows this part of the model. That means pronunciation is a little bit different from that one. So the probability vectors can be like, what is the probability of starting from this state to jumping into this state. So because 71 times, so approximately 0.7, so we take that probability of QB given QA equal 0.7. that is QB is our state here, AX, and AH is state the other, the phoneme is this one, other pronunciation model is here. And then we have this second one, 29 is about 3%, 0.3 out of 1, so probability should be 1 when you add these two. So it's a probability of QD given QA is 0.3. And now we have few other observations. That means at this point there are two observations of the acoustic signal. That means we have the acoustic signal recorded, and then we observe one acoustic pattern here and another acoustic pattern here. So probability of the observed sound at B, that means state B, can be not exactly equal to the that you might want to listen, but it may be about 0.8 probable that particular acoustic came. And similarly at C, we might be expecting a certain acoustic pattern, but we will get about 0.9% accurate the calculation of the vector. And then we again sometimes we get a similar acoustic pattern here, because we have only two timestamps. At this timestamp, the probability of this is actually y0 is the observation observing the acoustic sequence given qb, q1, y1 given qc, y0 given qd. This y0 is because we are still here, y0 and y1. y0 is the observation of this acoustic pattern at this point 0 and 1. Timestamp 0, timestamp 1 here is 0.8. So basically these two probabilities are same. And now we're going to calculate the total probability. In this model we represent phone states as qi's. We now break up py given w into py given q comma w and pq given w. Since the model above only talks about one word wof, we leave the w. We don't need to have this w condition there out of this equation. That means py given wi. This is the condition that we have to calculate py given w, which is the y given start ex ax v end, py given start h v end. That is, there are two paths, y start given this condition ax v end plus start given this condition h this way v. So we have two paths. So the first path is p qb given qa times p the acoustic vector at state b times the b to c jumping from state b to state c, and acoustic vector at state c. That means state c is here. Acoustic vector at this state is y1, this is y0. So y0 given qb during state b, and you get y1 at state c, plus probability of qd given qa, that is qd given qa, this jump here, probability of this one, and then getting an acoustic vector at this point is probability of y0 given qd at qd state. What is the probability of getting y0 vector, which we calculated already, so we're going to substitute there. And this is the jump probability from here to here, and the end at the end, so py1 given this one. So whenever you add these two probabilities, you should be able to get the probability of getting word off given a certain acoustic vector. So we listen to a certain acoustic vector and then tell that the probability of this word, this acoustic vector, to become equal to off equal to this much. So when you substitute the value, that is the probability jumping from state 1 to a to b is 0.7, and this one 0.8. Acoustic vector at this point is 0.8, then 0.9. So 0.8, 0.9, and the probability in between probability is 1. So 0.7, 0.8, 1, 0.9 plus the second root 0.3, and the probability at this point is 0.8, 1, and probability at this point is 0.9. So 0.3, 0.8, 1, 0.9. So when you add these two, get 0.72. That means the particular observation can have a probability of 0.72%, so to 0.72 to be that word to be equal to off. So there are just like that, we pronounce a word and tell the model to calculate the probability. So then if the probability is very high, that means the model tell, okay, this word is this. And in this particular case we only use only one word off, but and then we have to calculate these values depending using some experimental evidence. That is, what is the probability of getting q1 to q2, q2 to q1 or whatever. That depends on the states of the word and the pronunciation pattern. Yeah, 6.72. And actually it is for just simple word, but it can build up to a word recognizer, isolated word recognizer. That means the key component in the development was the integration of local probability values over the sequences. How do we get these probabilities? Consider using HMMs to build an isolated word recognizer. That means if you want to make a system that you call a word, tell number, and then dial auto dialer. So number 1 2 3 4, so you have 10 numbers to read. So this model should tell, whenever you tell number 1, it should tell that number 1 has high probability, that using the model it should be able to identify the pattern of number 1 and then tell the recognizer this is number 1. So how you do it? Basically assume that we have a vocabulary of n words to be recognized, and that each word is modeled by a distinct HMM. So this is the key point here. Each word can be modeled by a distinct HMM in Markov model. So further assume that for each word in the vocabulary we have a training set of k occurrences of each spoken word. That means we need to speak it for several times. Earlier we did it for 100 times, so we have to have several occurrences and then several observation sequences, one for each speaker, and then we put them in a model. Basically this is the model. Basically each word will have its own HMM model. So we have the speech, the recorded speech here, so we send it through the model, and then each model say we record 1, so it goes through 1. There are few models, that is word 1, word 2, word 3, word 0. So there are 10 words, 10 words that you're going to utter. So if you utter 1, that means it goes through all these models and then try to calculate the probability value. That means 1 will have certain phonetic value, so the phonetics will calculate the probability of that particular model and then give a value here. So depending if the word is 1, then if this is the model for 1, it will give the highest probability, and then from that you can select the word. For each word n in the vocabulary we must build an HMM, that is we must estimate model parameter that optimize the likelihood of the training set observation vectors from the word n. So for each unknown word which is to be recognized, the processing of the figure to the left is to be carried out, namely measurement of the observation sequence. Via feature analysis is followed by the calculation of model likelihoods for all possible models. That's a simple example of isolated word recognition using HMM. So that can be done by several experiments. So then there is a thing called viterbi decoding, how to decode the correct words, so which I will touch upon in a next set of lessons in HMM. Thank you for listening.